that's the diagram for a traditional operating system. So you have hardware on the bottom. Then on top you run an operating system. In our case, it's Linux-based. And there is a space in the main memory which is reserved for the operating system kernel, which is called kernel space. And you cannot modify directly data which lies in the memory section of the kernel space. And your software usually runs in the user space unless you are a kernel developer. And you are communicating to the hardware through the kernel using system calls which are wrapped in the standard C library. And your user processes are using basically these system calls in order to access the hardware. That's the basic way how operating systems work, explained in 3 sentences. So if you see virtual machines, here we still have the hardware. We have the operating system kernel. We might have some management processes running directly on the host kernel. And then the main thing is this hypervisor here, which basically creates a virtual hardware subsystem. And on this virtual hardware subsystem, you install another kernel and you communicate now from the user space to the hardware through this layer. First the kernel of your virtual machine, then through the hypervisor. The hypervisor itself is a user space process, and this uses the host kernel to communicate to the hardware. And that means actually the hypervisor and the kernel here are overhead, and that's the thing which Docker addresses. So if you have Docker, and basically this idea is not new. So on BSD there was a system called Jails, and before Docker evolved there was a system called LXC, the Linux Container extension, and basically Docker itself uses LXC in the background. And the idea here is that you are separating the user space into different sections. And the way how this is done is through 2 Linux kernel extensions. One is called C groups and one is called namespaces. C group stands for control groups. And that is an extension in the Linux kernel since version 2.6.18, I think, implemented by Google. And that allows to separate the user space into different sections by separating namespaces. So namespaces means for the file system. So you can separate a subset of the file system and assign this subset of the file system to this container. And also for the process tree. So if you do a PS tree, then you see all the processes on your system. And using that namespace extension, you can grant access only to a subset of this tree to a specific container. And on the other hand, control groups allows you to divide the hardware into shapes and assign that to containers. For example, assign only a subset of CPU slices or main memory or I/O bandwidth to a container. And this system was actually introduced by Google, so they got rid of all their virtual machines, and nowadays they are running only containers. And such a container starts really fast. So a virtual machine needs about 2 to 3 minutes if you have a good machine. And what do you guess? How long does it take to start a Docker container? Okay, it's around 30 to 100 milliseconds. It's really fast, so you can dynamically adjust the number of containers to your workload. And the thing is, there's no operating system being started when you start a container. There's just created a set of processes, and these processes are assigned to a control group and to a namespace, and that's basically all. That's LXC. That's what's LXC. That's the Linux container extension. And Docker has some cool things around that, which I will introduce later, and that actually made Docker so famous. So, and this is some of these components. So you have the Docker image. The Docker image is basically containing everything but the kernel for running your operating system. So inside the Docker container, of course, there's no operating system running, but we have learned here. There's the kernel used by the host system, but you can have all the files needed for your operating system in this image. Therefore, you can, for example, run an Ubuntu Docker container on a Red Hat server, for example. This image format is very handy in the sense of DevOps. This means this image is layered. That means every component you add to this image is a layer in the image, and you can basically ship around the image by layers. And that means if you change a little thing in the image in one layer, you only have to send this layer to somewhere. And to somewhere means you send it to a registry. So there is a central registry. The most famous is the Docker Hub registry. There you get public and private. The private you have to pay. And IBM has also a registry. And all the major cloud providers have Docker registries, public and private ones. And that's a repository for images. Of course, the largest is Docker Hub. And the thing is, if you want to run an image on your local machine, you have to pull this image from the registry. And if you modify that, you can push it back. But you are only pushing the layers which you have modified. We'll see later how that works. But that basically enables you to use these images in a DevOps cycle. So you have versions and releases of your code. And you can also assign this code to a very specific version of an image, and you can ship both together, and you know that both are fitting. A typical image, root image or base image is around 100 megabytes, and the stuff you are adding might be only 5 megabytes. So basically you can ship 5 megabytes and you have a complete virtual machine shipped around. And another component is the Docker daemon. Docker daemon is process which runs on your Docker host, which is implemented in the Go language. Anybody has heard about the Go language? That's a language Google invented, and all that cloud stuff is implemented in Go. So Cloud Foundry, Docker, OpenStack, Rocket, whatever, it's implemented in Go. It's basically looks a bit like Java, but it generates a binary. And that binary can run directly on operating system, and so it's an alternative to C without the problems of C basically. So this Docker daemon is managing all that containers, and the container itself is a running instance of the image. And basically a container then is just a set of processes which are running inside the container plus the configuration of the restrictions of these processes, of this process group. So as already said, this is an example of a Docker image. So you have a base image. You can use an empty image, which is called Scratch, and do everything on your own. But there, for every Linux distribution, there's a base image. They are also versioned. You can always say :latest, then you get the latest version of the operating system, but you can already specify the version you like. And then you do your stuff, install a database, install a Java runtime, install your application, and then you have your own image, and that you can ship around. You can send it to somebody, or you can push it back to any registry and just give somebody access to that registry and to use it. There are two ways of creating such images. One is starting a base image, attach to your image, basically get a shell on your image, and no, that was not correct. Use the image, create a container out of the image, and attach a shell to this image, do your modifications, and then outside the shell you can say docker commit, and then the container ID, and then all your modifications are stored in the image. But that's not the way normally the people are doing it. The people prefer a way to do it. This is called Dockerfile, and that actually is like a shell script which creates the image for you. And the advantage on the Dockerfile is you can create a Dockerfile, Docker image based on a root image you trust, and you see exactly what's inside there. So you can double check what the maintainer has done, and you can also contact the maintainer and say, oh, this is maybe a security threat. If you have the root password here in plain text in the Docker file, please change that or something. You can also version these Docker files and even ship them around, and they're even smaller than the image itself. And that's basically a bit more complicated than a Hello World example, but I think it's a good way to explain this. Using this Docker file, you can create a Docker image based on Ubuntu and add SSH support to it, and basically then start it and log in to the image using SSH. So I will just explain the keywords a bit. So these are comments. Then you have from, that's the first actual line which tells you the root image. This can also be scratched and it would be an empty image, but now it contains an empty Ubuntu installation. That's an optional thing, maintainer. And then the run commands, basically they are executed in the stage where you build the image. So here we just update Ubuntu and we install OpenSSH server and we configure as OpenSSH server. For example, that we permit root login. And this way you basically see exactly what's going on here. And then another important keyword is expose. So per default, no ports are open or accessible in a Docker image, and expose allows you to tell the Docker daemon later which ports he shall open. But that's not the firewall here, that's just the metadata. You can decide or override this configuration. And then the last line here, cmd, is the command which has to be executed once the image is started. So from here to here, it's executed during build time, and the last command is executed when you actually create a container out of the image. You can also override this command if you like. And now we will just, yeah? Yes. Expose is meta information which tells the Docker daemon later which ports on the container should be open to the public.
Okay, so if you want to open dispose by default into your image itself.
Yes.
Okay,
yeah.
So,
but it's only meta information because I just show this later, but you can say dash capital P. That means read the port meta information out of the image and open all the ports. Or you say dash small p, and then you actually define all the ports you want to open. As I said, it's not the firewall configuration. Capital P takes the information from the container, and small p overwrites this. Overwrites this configuration. Yeah. So, so I will demo all this stuff now, and then later we will do it together. So now we create this image from scratch. I have prepared this already. So now I enter full screen, and I should increase the font size a bit. Yeah, that's okay, no? So I've created this Docker file, or to be honest, I've copied this Docker file from somebody. And what I do now is I will create a Docker image out of this Dockerfile, and that's pretty easy. I say Docker build, and I give this image a name, University of Berne, for example, and then I say dot here. Dot means search for the Dockerfile in my current directory, which is present here, which you see here, and I say enter. That was it already. So here it says from Ubuntu. He created one layer, and then you see he's creating subsequent layers for every command basically I'm running. At the end, he says successfully build this image. So I can say Docker. Yes. And since I'm recording this session, you don't have to make notes. You can see that later. You say Docker images. Oh, there are too many, so I will grab this one here. It's the one I've just created. So it's 5 hours ago because I didn't make any changes, so it use the cache. I think I can use -F for force or some empty cache option, and then he will create it from scratch. So since, yeah? Yeah, that's I've explained just now. Because there's a cache, and since I haven't changed anything in my Docker file since 5 hours, he won't overwrite it. Therefore, it's 5 hours ago. So now I have this Docker image in my local repository, and I can just start it now. I say Docker run. Now I'm using this -P option to read this meta information about the ports. Yeah.
About the ID, I need to have a different ID for each user.
You need a unique. Yeah, that's something I'll explain later. Okay. So because you can assign multiple IDs, no, you can assign multiple tags. So this on the left-hand side are tags to the image, and this is a unique ID. So the ID is unique, and the tag can be different. That's used to use the same image in multiple clouds or repositories. That's what we'll see later. So I say -P, then I have to say -d. That means daemon, that actually the command comes back and doesn't block. Then I have to provide I could use the tag or the image ID, that doesn't matter, and I think that's everything. Yes. So that's unique ID of the container. And now I can say Docker ps. And now you see here, that's the image running in the background. And you see here the name. So that's the container ID. So that's not the image ID, the container ID. If I would have run a second one, then it would have get a second ID. I have not tried this before, but I think I no, I haven't done. So you could, in theory, start as many containers in parallel as you like, yes? I can show you. I'm not happy that this doesn't work. Give me 1 second. I forgot basically how to do that. That's all. Okay. Because yeah, you get automatically a second container ID assigned. So let's start 10. That you see how fast this is. I haven't tried this before, but it should run without problems. So for the in you see it's less than a second. without with a complete round trip. So if I say docker ps, you see here I have now 12 images running. And to come back to your question, I just omit this p-value, and then you can make out that's the last one without the p-value. And you see here the port is open, but you won't be able to access it. If you put the p-value, Docker automatically creates here a mapping from the port of your local interface to the internal port of the container. And actually I will just use this to connect via SSH inside the container. You see here, that's not working like this, SSH. So localhost means that's the IP address of my host system running all these containers, and the Docker daemon created the IP tables firewall rule to forward this port to the internal one. And I used the password which is in the Dockerfile. So what I've done wrong now, I don't know. Where is my password? Screencast, okay. Let's try this again. I have now to check what I've done wrong. Use another container. I'm an idiot, sorry. This one, I have to use the -p option. Now it works. So now I'm inside the Docker container, and if I enter ps, what do you think what happens? Nothing? Yes, I see SSH and I see bash. Oh, I don't see SSH. Why don't I see SSH? Now I see SSH. SSH, bash, and ps. Yeah, so you see only 4 processes inside the container. And if I now go to the host system, I should see these processes of all containers. Let's give it a try. Okay, you see all these processes are running in one container. So let's get rid of all of them. So let's say docker ps, and then say so these are the container IDs, and I say for container ID in so now it's the command to actually shoot the container, not to stop it gracefully, just to shoot it, because I won't destroy anything since there is no persistent data in the containers. So I say docker rm force, and then container ID. So see, it's really fast. Now it should see nothing. All the containers are dead. Okay. So you like Docker? Okay. Still not convinced? Okay, so that's the local round trip. So that I've done, yeah. So Docker has some more components because it's fun to do that, but if you use all these components, it's even more fun. So there is Docker Compose. Docker Compose allows you to define a topology of multiple Docker containers and their interaction, and deploy such a topology with one command. And that's something I will show you now. And I will show you that using Flink. Have you heard about Apache Flink? Never? Have you heard about Apache Spark? Okay. So for those, have you heard about Apache Hadoop? Okay. So first Google for Hadoop, then for Spark and for Flink. So Flink is the newest thing, which actually is developed in Berlin, in Germany. So I think that's the first top-level Apache project outside US. And it's a data processing engine. And the cool thing is it consists of a master and it consists of workers. And there is a Docker package for that. And there's one Docker image for the master and n Docker images for the workers. And using Docker Compose, you can just start such a cluster with one command, and that I will show you now. So Flink, Docker Flink. So I will show you now the two Docker files which are used here. So you see here, Ubuntu Trusty is the base image. We do update, install, blah blah blah. We installed Java from Oracle. Then we set the root password. So that's a common technique, it seems. We expose port 22. And basically we start, no, we don't start anything. That's the base image. And then we have the Flink image, and the Flink image now doesn't rely on the base, on Ubuntu, it relies on base. So that's the extension of that image, and it does some additional things like keyless, passwordless SSH authentication between the containers, and actually downloading this Flink package and installing the Flink package. And task manager means it's a worker starting the worker. So this container, when it is created and started, will actually run a Flink worker, and this is the corresponding Docker Compose file for this cluster. And there's one master, and this master will start a job manager process inside the container. And therefore, the whole topology is described, and also all the commands which has to be executed. And I just will do this now. So I say build.sh, and that's basically doing nothing but building two Docker images out of these two Docker files. Okay. So now I say Docker images. Since I have too many, I say grab base and grab Flink. And you see here there's a Flink and a base image here. 17 hours ago, it was yesterday evening, I have changed it. So since I haven't changed it today, it's still the version from yesterday. So what else? So I have now created these images, and now I can just start. The whole topology using one command, as promised. So now I've started a topology of 7 containers, 6 workers, and 1 master. And I now will show you how this looks like in the Docker shell. So let's say, so I'm again root on the Docker host. Now I'm root on the Docker host. I say Docker PS. And now you see here, that's the master. And you see here also all the ports which are exposed. and then you see the workers. Okay. Now what I will do is I will create a SSH tunnel to forward one port from my MacBook inside of the master container in order to access the web interface. So I will do this now. So what I do now is I say SSH root at. So that's the IP address of the Docker host. But as you can see here, the SSH port is mapped from port 220 to port 22. So I have to access port 220. And the password is secret. So now I'm inside the master container, inside the Docker host. Yeah? That's basically done by the name. You see here, Docker Flink Job Manager 1, that's the master, and Task Manager 1 to 6 are the slaves. That's one way to distinguish it. And the other way, of course, you see a lot more ports exposed by this container. Not necessarily, no. You should use the name, because I show you the Docker Compose file. The Docker Compose file, you say here the image should be called Job Manager, and this way you can identify it. If you would start two topologies, then you would get two job managers, and then it's harder to distinguish between them. But yeah, that's the way it works. So now this runs, and I just want to show you now the web interface. Therefore, I have to port forward 8080 to 8080 and 8081. And now in theory, I should be able to use my browser, say localhost 8080. Okay, and I see now the dashboard of Apache Flink, and you see here 6 task managers. And now I will do a fun thing. I will scale this down. So I say Docker Compose scale task manager. Oh, I will scale it up, that's more fun. 10. Task manager. You see, if I say Docker PS, then I've created more workers, and now I should see in a couple of seconds, take some time, that I have 10 task managers here. Yeah?
This is obviously nice for distributing.
Yeah.
So how many cores can individual Docker image use? Multiple cores or one core?
That's doesn't matter. You can specify that. There's an option called CPU something. CPU shares. So your CPU is the whole all the CPU cores on your host are divided into 1024 slices or shares.
Okay, no matter how many you have.
Yes, and then you can assign a number of shares to each Docker. And that's basically opportunistic. It means if nobody's using the CPUs, you get the whole system. Mm-hmm. But in case you have concurrency, then you get the maximum of 2. Yeah. Okay, so now that's pretty cool. But the thing is, it's boring if you just have one node. it's more fun if you have multiple nodes, and that's Docker Swarm. And Docker Swarm basically is really fun because Docker Swarm is acting like a Docker daemon. So the interface, the REST, so it's all is working through REST. The Docker daemon is opening a port and HTTP listener, and you communicate with the Docker client to the Docker daemon using REST. And the Docker Swarm daemon also implements the exactly same API. So you have no idea if you are talking to a Docker daemon or to a Docker Swarm daemon. But the Docker Swarm daemon is talking to multiple Docker daemons in the background. Then these multiple Docker daemons are running on different nodes. So you think you are running against one machine, but you are running against a cluster. And the cool thing which IBM did here in this case, IBM used Docker Swarm, and they implemented a container placement optimizer, which they will open source hopefully soon, and basically provide this as a cloud service and charge based on the memory consumption. So you can run one image with 1 GB, or you can run 1,000 images with 1 terabyte. And the cool thing is, since they start in less than 1 second, you can adjust the number of workers based on your workload. Okay? So that's the toy which I'm playing currently with. And the last thing to mention is in this ecosystem is Docker Machine. And Docker Machine is a system to install the Docker components on any Linux system, on any data center. So you can install it in a virtual machine on your laptop, or you can install it on the IBM cloud or Amazon cloud, or in your data center. So that doesn't matter. And in addition, it configures the local Docker configuration for you, that you just execute your commands against these newly installed components. And yeah, that's basically what I wanted to mention there. Yeah, and now I will just show you how to do this in a Docker Swarm environment on the cloud. So what I do now here is, so let's stop this Docker Compose thing here, and in parallel I say now Docker images, grab any Berne. So now I have this image locally. Now I have to push it to a cloud registry, which I will do now. So I will explain you these commands in more detail later in the hands-on session, but I think I don't have to log in. I did that, so let's try this. So I have the image now locally, and now I want to push this image to the cloud. So you see here, that's Bluemix, that's the name of the IBM cloud. I say here push. And the cool thing is I have done this already, and this just finishes in a couple of seconds, because every layer it will determine that it's already in there and skipping. We can do a little thing just to see how this works. I have not tried this, but let's do one thing. Let's create a folder. So we create an additional folder in the image. That means if we build the image, building too many images. So if we now say Docker images, so you see here, now you are also convinced, I've built it 10 seconds ago. And you see here it's getting a new image ID. That means actually I have to retag. Oh my god. This new image ID, or I can also use Berne, because Berne now points to the new image ID. And now I tag this, I think it was Berne test in the cloud. I have to use -f because otherwise it won't get overwritten. And if I now push the image again, okay, docker push this one, then you will see that this one layer which we have created will be pushed. So that's the layer actually which has been created based on the create mkdir. Okay, it will also push all subsequent layers because these are diffs between. So if I change a layer in between, all the subsequent layers are changed and they are repushed again. Yes. So now it's in the repository. What I can do now is instead of Docker, I say, okay, maybe I should explain this a bit more in detail. So I now log into the cloud. But I cannot give you a complete cloud education here. Therefore, you just have to believe me what I'm saying. So I log in here and so now I'm logging in to the Docker Swarm instance in the IBM Cloud. And I can do two things. I can use this this tool here, or I can export 3 environment variables, and that basically points my local Docker client to the Docker Swarm API running in the cloud. But I won't do this here because then I cannot switch between the local and the remote one. Therefore, I will use these commands here. But basically, CFIC takes the same arguments like Docker. And if I say CFIC, I'm using Docker Swarm in the cloud. And if I say Docker, I'm using my local. So you see here, if I say Docker images, these are the images on my local Docker host. If I say CFIC images, these are all the images in my private repository in the cloud. And as you can see here, about 1 minute ago, I have pushed this new image into the cloud. Yes, you know CFCLA. Oh, I didn't expect somebody know that. So CF stands for Cloud Foundry, and Cloud Foundry is an open standard, open source environment for platform clouds. And the platform cloud, basically, in contrast to infrastructure cloud, is that on an infrastructure cloud, you have to install your software on virtual machines. In the platform cloud, there are high-level services like a database or like this Docker Swarm or whatever is there as a service. And Cloud Foundry is an open standard, and the IBM Cloud is running on this open standard called Cloud Foundry. And IC is a plugin to this, so I can use the Docker Swarm out of this. So what I will do now is I say CF IC, which is the same like Docker run, but now on the cloud. I say run. I have to tell which image. Oh no, first I have to tell, give it a name. And I say -p to expose all the ports. Basically this means port 22. And what I've done wrong. Something. Give me 1 second, please. here. Okay, so I've mixed and matched the parameters. So this should now work. No. Let's just copy the running one and modify this. So, go back to this one, and what I have to change is this one. So okay, so and now if I say cf IC, which is the same like Docker but now remote, and ps, then I should see this container now 18 seconds ago. You see I have tried this in the train 1 hour ago. So and now what I can do now is I can assign an IP to this container. So IP request okay, that's the so let's do cfic rm force this old one. So I should see only one image. And I say cfic IP list, so I get a list of all IP addresses, and I will just free all the so I will free this one, release. Now I can request a new one. So I obtain this one. And now what I can do is I say cf ic IP bind this IP address to this container. Bind, not bind. And if I now say cfic ps, I should see the IP address and the port mapped to this container, which is the case here. And now I can say SSH, and this is running on port 22 because it's a public IP. I'm alone on this IP, and I can of course use port 22 for my container, which is a very cool thing. I don't have to do any mappings again here. And I say just IP, and it's root, and I say password. So now I'm inside the Docker container in the Docker Swarm cluster in the IBM cloud. And I also see here these processes which I've seen on the local machine. I think that's all for the demo part. Yeah. And I think now it would be fun to have some hands-on. So for those who don't want to do the hands-on thing, feel free to leave and drink coffee, have fun. And the others which are staying, I will help you installing the Docker environment on your laptop. And we can do anything from creating a hello world little thing up to Docker Swarm, Docker Compose, or something like that installation. Okay, let's open now for questions and then do the hands-on part. Any questions? Yeah.
The media I noticed that you run all the replicates inside of the Docker instance. Is that correct?
No, it's a VMware Ubuntu.
Okay.
Yeah.
My second question was, So kind of by default, you kind of run all the commands inside of the machine as root. Is that the recommended thing to do? How can you get around it?
I think you can somehow get around, but it's a complicated configuration, and I have not gone through that.
And there's no security issues with that?
Yeah, Docker is not the most secure thing, so there are some security issues which are currently addressed. And yeah, therefore there's a second project evolving at the moment, which is called Rocket. Maybe you've heard about Rocket. So that's there's Apache Spark and Apache Flink, there's Docker, there's Rocket, and the Rocket developers say it's much more secure. But the thing is, it doesn't matter, because a couple of days ago, IBM and Microsoft and VMware and EMC and Amazon, they announced an open alliance for technology-independent cloud standards, and so it doesn't matter what will be the actual runtime. And also, for example, I've shown you here Docker Compose somewhere. Yes, Docker Compose. Yeah, Docker Compose. No, sorry, Docker Swarm. And Docker Swarm is bound to the Docker technology, but there's another provisioning system which is called Kubernetes from Google, which is container agnostic, and also IBM has one which is called Smart Cloud Orchestrator, which is container agnostic. So the trend is to be container agnostic. So a smart orchestration system can provision Docker containers, Cloud Foundry containers, virtual machines on Amazon, on OpenStack, on IBM, on your local data center. That shouldn't matter at all. Yeah. Vagrant is not for containers, that's for virtual machines. But more or less it's a bit the same like Docker for virtual machines. Yeah. So it has out-of-the-box support for VMware and VirtualBox and some 2 or 3 other things, KVM. Okay, maybe we do a 2-minute break and then continue with the hands-on section.